Okay, so today we're starting actually what I consider one of the high points, or actually maybe two of the high points. This class, in my view, has three high points, three punchlines that we're building towards. So the whole learning about finite state machines, and then push-down automaton, and then Turing machines. We're building up the machinery that's necessary in order to establish, or at least present, three critical ideas in the theory of computation, the three high points. And today I'm going to definitely present one, and then start building up towards the second high point, which probably we'll do on Thursday. Okay, so the Church-Turing hypothesis or thesis or theory or whatever. So Church was a logician in the 1930s, Turing the 1940s roughly, and they were trying to formalize what it meant to be able to compute something, what an algorithm means. So today, we all very used to thinking about algorithms and writing programs and using computers, and it may not even seem necessary to have a definition of what an algorithm is. But in the 1930s and 40s, they didn't have computers yet, and certainly they had algorithms. Algorithms go back thousands of years as some procedures, some kind of, I shouldn't say mechanized, because they weren't mechanized then, but anyway, mechanical kinds of procedures for computing things. And like greatest common divisor, yeah, GCD, which you all learn in some earlier course, and various things that were established by algorithm. But there really wasn't a formal definition, and therefore you couldn't prove things about the nature of algorithms. What could algorithms do? Is there some limitation to what's doable by an algorithm? That's what algorithms can't do, or how quickly can algorithms solve a problem? Are there some problems that are not solvable by an algorithm but are solvable by some other kind of mechanistic device that you wouldn't call an algorithm? And so on. And they tried to formalize this, even though there weren't computers and there weren't a lot of algorithms, certainly not as many as there are today. And I can't actually tell you exactly what Church was saying, but what Turing basically said, and this is the viewpoint that we've come to take, is that an algorithm, what an algorithm is equivalent or essentially defined by a procedure that can be implemented on a Turing machine. Okay, so the Turing machine, and that was defined by Turing, encapsulates what an algorithm is. Anything that can be done on a Turing machine is an algorithm. Anything a Turing machine can do defines a particular algorithm. And this is a thesis. This is not something you can establish as absolutely true once and for all, not like a theorem. It's his Turing, and equivalent to what Church was saying, although in different language. This is his assertion and formal definition of what it means for something to be an algorithm. Now, since this was articulated back in the 30s and 40s, lots of people have looked at this in more detail and come up with other formalisms for what they said was an algorithm. No, I think an algorithm should be defined this way. And then other people, or maybe the same person, have shown that that's actually equivalent to what can be done on a Turing machine. So people have thought of lots of different kinds of, in some cases, weird formalisms for what they think an algorithm is, to some extent with the intention of showing that this wasn't adequate. But then again, somebody would show that, yes, it is adequate. Your formalism of what you think an algorithm is actually can be. Anything that can be implemented on your formalism can be implemented on a Turing machine. And we've done a little bit of this where we said, well, what if we have multiple tapes? What if we have multiple heads? What if we have, maybe there's some language that can be recognized by a Turing machine with some additional powers. If there's such a language like that, then the problem or the procedure of recognizing that language is implementable on some machine that seems sensible as a model of a computer, and yet it's not implementable on a Turing machine. That would make this thesis wrong or irrelevant. But in fact, all of those kinds of embellishments, multiple heads, multiple tapes, multiple dimensions of the tapes, and so on, have all been shown to be equivalent to just the plain old vanilla Turing machine. One head, just a one unidirectional infinite tape, and so on. Finite control in the kinds of transitions that Turing machines have, and so on. So this thesis is held up now for 80 years, despite various people trying to show that it was incorrect. So, and modern computers look a lot like Turing machines. And in fact, part of that is that Turing had some hand in sort of designing early computers. And we'll see another justification for this thesis a little bit later today, probably. So this is a thesis, but it's the one that we accept in this class as what an algorithm is. It is any procedure. Now you can ask, what's a procedure? Anything that's describable in finite space that says do this, okay, go back, do that, etc. Anything of that sort that you can ultimately implement on a Turing machine, on a specific procedure is implemented on a specific Turing machine, then we call that thing an algorithm. Any questions about that? And why do we want this? Because we want to reason about algorithms. If we don't have a clear definition of what an algorithm is, then we can't really prove things about what is doable by an algorithm, what's not doable by an algorithm, how much resources does it take to do something by an algorithm, and so on. If I just say, okay, my algorithm is I take the string as input and I write it down backwards, and then I stick it in my ear on this piece of paper, and I run to the top of Mount Tamalpais, and I wait for divine inspiration to tell me what the answer is. That's not an algorithm, okay? You can't implement that on a Turing machine. And so this definition has some utility, but it avoids things like I just mentioned. If that's your procedure for solving a problem, yes, that goes outside the domain of this whole theory. But for the most part, that's not how that's not how computation is done. All right, there have been some challenges to this, principally, and now I'm talking about stuff I absolutely don't know, but hasn't stopped me so far in this class. There have been some challenges to this, principally from physicists who come up with various ideas, like you can take a Turing machine, standard old Turing machine, and throw it or somehow propel it near a black hole, so that when it comes around, there's a moment in time or something where the Turing machine can actually do infinite computation in what appears to us to be finite time. Or I don't know. I'm sure I'm getting this all wrong. But when you go outside of that domain of sort of our standard three-dimensional Newtonian world, then there are some proposed challenges to this. And then the whole world of quantum computing is serious and has really gotten a lot of serious attention. But people have proven that that doesn't actually get you outside of the Turing machine model. It may speed things up dramatically, but not infinitely. And so we're still in the Turing machine world. Okay, so that's the first high point of this class, or what your the real takeaway message that you should have with you for the next 80 years if you continue on. And it's a cultural thing. It's, is this going to really help you write the next killer app, or the next computer game that everybody must have? Probably not. But it crystallizes and formalizes hopefully your notion about what an algorithm is. Okay, the next high point that we're going to prove, and I'm going to start the mechanics and start talking about the tools for this today, is to prove that there are languages that are not first of all, languages that are not decidable, and then we'll prove there are languages that are not recognizable. And that means that there are problems, essentially, that have no algorithms, that there are problems that are not solvable by algorithms. So it shows the limitations of, even though we have a formalization for what an algorithm is, we can, and now, maybe I should say, now that we have a formalization of what an algorithm is, we can actually make assertions like that there are problems that simply are not solvable by algorithm. There are problems that are not solvable by computer. And actually prove that. That's not just a hand-waving assertion. It has a tangible meaning and a proof. And then we're going to do that this week. We probably won't get to any of those proofs today. We'll just build up some of the mechanics of getting to some of those proofs. But that's the second high point. The third high point comes later and needs some more build-up. Okay, so let me, this is the Church-Turing Thesis. Let me remind you of a definition that we've seen before of what it means to be, for a language to be decidable or recognizable. Well, actually, this is sort of almost circular. A language is decidable, or sometimes called Turing decidable, if some Turing machine decides it. Well, okay, what does it mean for a Turing machine to decide the language? It means that there's a Turing machine, we'll give it M, such that when M is fed input W, M accepts W if W is in fact in that language, and M rejects W if W is not in the language. Okay? So M is a decider. It decides the language L. So whatever input is given to W, M will either accept or reject. It always terminates. And it will accept if W is in L, and it will reject if W is not in L. Okay? And that's what it means for a language to be decidable. Well, recognizable, or Turing recognizable, a language is recognizable if there's some Turing machine recognizes it, There's a Turing machine M such that when M is fed input W, M accepts if W is contained in L. And then the rest we take out. Okay? So so this is now I'm talking about recognizable. Okay? So your notes have got to be dynamic. You have to be able to separate what I did when I was talking about decidable and what's up there now, which is for recognizable. Okay? So maybe I should strike that, and strike that. Okay? So this is a definition for recognizable. Language is recognizable if some Turing machine recognizes it, and that means, more particularly, that there's a Turing machine such that when M is fed input W, M accepts W if W is in fact in the language. Now, what does it do when it's fed an input W where W is not in the language?
Rejects or goes for error?
Yeah, it either rejects, which is fine, or it doesn't terminate. Okay? So I can put that down. When W is not contained in L, then M either rejects W or doesn't terminate. And obviously, you would prefer to have a Turing machine that can decide a language instead of a Turing machine that only recognizes it. But recognition is still something of value. Okay. Now I want to define some languages that are decidable and show that they're decidable. And then later, the high point, as I mentioned, will be proving that there are languages that are not decidable. Not only proving the existence of languages that are not decidable, but actually exhibiting some specific languages and specifically proving that those languages are undecidable. But we're going to start out with languages that are related to DFAs. And this will also introduce a kind of a new viewpoint that is really necessary for when we prove that there are languages that are undecidable. Okay. This is a language. What is it? What are the elements of that language? They're going to be objects that look like this. Okay? B is a DFA. Well, what do we feed into Turing machines? What do we feed into? What have we been processing this whole course? Or strings. Okay? So when I say that B is a DFA, how do you put a DFA as input into a Turing machine? Well, a DFA is specified by its most essential specification is its transition rules, right? Which are just strings. Okay, so B, it's a DFA, and what is it? How do you specify it? Well, we need to know what its alphabet is, we need to know what its set of states are, and we need to know the transition function, Q cross sigma into Q, right? That's how we can formally specify any DFA by, oh, no, that's not quite enough, but we need the start state and we need the termination states, or the accept states. Okay, but this is how we formally specify any particular DFA, right? And these are all just symbols. So this is you can think of this as a string that's, the alphabet is a set of characters separated by commas. The states are described symbolically. And the transition rules are also just strings, really. Okay? So I can describe a particular DFA in terms of a string. Okay, so this is just a string, or this can be written out as a string. Now, when I write this out as a string, I'm going to probably need some additional characters like delimiters. Something that says this is where my description of the alphabet ends, and this is where my description of the states begins, and here's where it ends, and this is where the transition rules are, and so on. So I can have a string over some alphabet that's that can write these and clearly specify them. Here I'm actually being more detailed than what's in the book. I think the book at this point just leaves it to your intuition that, of course, you could write down, when you write down the specification of a DFA, that's just a string. And if you need additional delimiters and so on, that's also just part of a string. So does everybody get this idea? This is a new viewpoint, but it's really critical for what's coming next. That I can input the description of a DFA to a Turing machine, okay? Because the description of a DFA is written symbolically. Anything that's written symbolically can be turned into a particular string, okay? If a DFA was a physical object made of metal and plastic and gold and whatever, pushing that into a Turing machine would be difficult, okay? I mean, it just wouldn't, we have no mechanisms for talking about that, but certainly inputting a string. Okay, so this is a string that specifies the DFA B. And then W is some particular string where W is going to be from sigma star, okay? So this is some particular input intended for B. So this is what's in this language is the set of pairs where B specifies some DFA and W is some input intended for B. And this particular string is in this language if B accepts W. Well, B is a DFA that accepts W. Okay? So this is maybe, one step higher or additional step in terms of our abstractions. Before we had a DFA that takes in a string W and accepts or rejects. And now we have a Turing machine that takes in a description of a DFA that takes in a W. Okay? So has anybody seen examples of a program that takes in another program and does something with it?
Functions, but not whole programs.
A what?
Functions, but not whole programs.
A function? Well, yeah, okay. You can have programs that take in a function and then do something with that function. Yeah. A what?
Like a debugger.
What's the last word?
A debugger.
A debugger. Yes, possibly. Yeah, a debugger is an example of a program which takes in another program as input and also usually takes in input to that program, and then the debugger is looking at that program on that input to give you some valuable information. Other examples?
Shell script?
A shell script. Yeah, I'm not sure how that fits. Probably does, but a what?
There's an interpreter.
Okay, yeah, the two big ones that I was looking for are interpreters and compilers.
Well, that's what he was saying. Shells are interpreters.
Oh, okay, an interpreter, yeah. So the interpreter is a program, and it takes in the shell script, which is also a program. Now, there's not necessarily the input to the shell script that the interpreter, yeah, actually will. Anyway, yes. And a compiler also, well, the compiler doesn't have the input to the program. A compiler is a program which takes in another program and operates on it and puts out yet a third program in a lower level language typically. There are even compilers that are written in the same language as the programs that are going to be fed to it for translation. I don't know why that should feel odd. It seems, now that I say it, perfectly sensible. But I remember when I first heard that, that sounded very paradoxical. But, how can anyway. Okay, so this notion of a Turing machine taking in a description of a DFA and what the input to that DFA is, and then this Turing machine doing something on that input. That's analogous. That's sort of similar to this whole notion of a program that takes in as input another program and input to its program. Yeah, debugger is a very good analogy. And what this, what the Turing machine is going to do is decide whether the DFA B accepts W or rejects W. Okay, so this is a theorem. This language, DFA, is decidable. Okay, and just in more detail, that means, i.e., yeah, there is a Turing machine that can take in input of the form and decide if B accepts W. Okay? Now this Turing machine, it's not built specifically for B, because B is any DFA. It's a description of any DFA. When you build M, we don't, whoever builds M, whoever specifies that Turing machine M, doesn't know B or have in mind any particular DFA. This is going to be a Turing machine that can take in any description of any DFA and any of its input and decide whether B would accept W or not. Anybody have any ideas of how you would build this M? So again, what's coming in on tape? What's the tape for M? So here's M. And its tape starts with a description of B. It starts with all of this stuff. What's the alphabet, and then some delimiter symbol. I don't know what it's going to be, but some symbol that's not, that's built into here as the delimiter. And then some description of the states, and then description of the transitions, and so on. Q0, F. So it's got a formal it's got a formal specification of what B is, and then it has to see what W. It has to know W. Okay, so it's got a description of a particular DFA and a particular W. But now my question is, what's in M? What's the mechanics of what this Turing machine is going to do, or how can it do it? Well, okay, yeah.
Have it check against the rule of B every time it accepts an input.
Okay, that's sort of the beginning. So I think the idea, the word I was going to use here to stimulate your intuition, stimulate your intuition is to simulate. Stimulate to stimulate. Simulate to stimulate. Okay, at any rate, just a bad play on words. Okay, anyway, we're going to simulate. We want M simulates B on input W. So we have to think of, how do you build a general Turing machine that can simulate a specific, or it can simulate a DFA when given the description of the DFA on input W. Okay? So inside here, we've got to be kind of rules like, well, let's run over and find what the next character in W is. All right? So one of the kind of things we can do, again, we have these delimiter kinds of things that tells us where W begins. So like the Turing machine could certainly have rules in it that would run over until it finds the first character in W, and now it's reading that, and it can turn that into a space or put some mark on it which says, now I've read that. And so it is looking at that first input. But what rule should it execute? Okay, so it's got to have a state in there that its states have got to somehow remember what its input was while it goes back, what character it's looking at while it goes back and tries to find the appropriate rule. And it needs state transitions in it, general state transitions of the type that Turing machines can have. You can't make this a more powerful machine or more powerful sounding machine than what a standard Turing machine can do. It's got states, it's got its own transition rules, and those have got to encode the logic of going back over and looking at the rules in here and also remembering what state it's in and what state the DFA is in. Then looking through the rules to find the one that's appropriate to what state the DFA is in and what input character, single character the DFA is looking at. All of that can be encoded into states. And the key is that the number of states in, actually the key is, I don't know. It sounds difficult and something you should give some more thought to, and the book doesn't give any thought to it. Of what really, how do you build this thing to look through here and decide what was going to go on? I was about to say the key is that Q is finite, which is true. For any particular DFA, Q is finite. But when you build M, you don't have any a priori bound on how many states the DFA is going to have that you look at. So it's something I need to think a little bit about too, and you should as well. That you can actually build a Turing machine with the regular Turing machine kinds of transitions that can do this general simulation. At the moment, it isn't completely obvious to me how that goes. Okay. All right. But at any rate, the way this theorem goes, the proof of this theorem is the book just essentially asserts that, yes, of course, by now we all have enough intuition about Turing machines to be able to see that, yes, of course there can be this Turing machine that can simulate B on input W. And that's what this Turing machine is going to do. It's going to simulate B on input W, and if B in the simulation accepts W, then M will accept. It will accept. M accepts its input if the simulation of B on input W, if, I should say, during the simulation of B on input W, B accepts W. And it rejects this if during the simulation of B on input W, B rejects W. Okay? So the hard part of all of this is how does the simulation actually work? And I'm going to think about that some more too, and you should do that as well. Okay, so this language is decidable, and let me give you some more examples of other things that are decidable. NFA is decidable. There's a Turing machine that can take, there's a non-deterministic Turing machine that can take input of that form and decide if B accepts W. Okay, what's the proof of this? Assuming that our previous theorem was actually proven okay, to everybody's satisfaction. What then is the proof of this?
They're equivalent.
You what?
They're equivalent.
Yeah, or they are equivalent, okay, and so mechanistically what we can do is we can convert any NFA to a DFA, and that conversion is also something that's got to be doable by a Turing machine. So if you look at the algorithm for converting an NFA to a DFA, you should be able to see how you could convert that algorithm to something that a Turing machine can do. Church and Turing told you that you can. You can succeed. You will succeed. And if you can prove that you can't succeed, you'll be the ones who've shown that the Church-Turing Thesis is not true, okay, after 80 years of people trying. So the algorithm that converts an NFA to a DFA can be implemented on a Turing machine. And so the proof of this is, well, build a Turing machine that does the conversion of an NFA, any NFA to a DFA. And the NFA, the description of the NFA comes in on a tape, and the specification of the DFA is what's written as output. And then the Turing machine erases anything left of the input. And so what it has on its tape that it created is the specification of the DFA that's equivalent to this NFA. And from that point on, what does it do? Well, at that moment, it has a specification of a DFA on its tape, and it still has the W that was written. I said it actually it was going to erase anything left of the input, but it shouldn't erase W. It should only erase parts of the description of the NFA if they're still sticking around. So at that point, we have a description of a DFA that's equivalent to this NFA, and then we can invoke the previous theorem that says that a DFA is decidable. Okay? That step, by the way, of using a previous result, of taking the thing we want to prove now and showing some details of it until that problem resembles a previous problem or a previous theorem that we have, and then saying, okay, we already have that previous theorem, and so we can use that. There's a general name for that style of argument. What is it? Proof by, not induction, contradiction, construction. What you've ever seen this idea? What? Reduction, yeah. So is that what you said? Yeah. Okay, proof by reduction. Okay, so we've reduced this problem, or this theorem, to a previous theorem that we have, DFA, and at that point we don't need to go into the internal details of how this was proven anymore. We can just invoke it. Okay, so reduction is a very powerful general technique, and we're going to use reduction much more explicitly in a later part of this class. Not today, but this course, and that's why I want to take the moment to point out that this is reduction here. So to maybe firm up the notion of what reduction is, the following story is often told. You're in a kitchen, and you have around you pots and pans and a sink with running water and a stove and so on, and your problem is to boil water. So how do you solve that problem? You take a pan, or pot, or whatever, it's empty right now. You fill it up with water, okay? You put that on the stove, you turn the stove on, you wait 5 minutes or whatever, and the water's boiling and you've solved your problem. Okay, so we have that solution. Now we have another problem. You're in the kitchen, you have a pot full of water, okay? And your problem is to boil water. How do you solve that problem? If you solve it by reduction, what do you do? Nobody getting the idea yet? Yeah, everybody's getting the idea, but nobody wants to say. obviously, by reduction, you take your pot full of water and you dump out the water. Now you're back to a situation where you have an empty pot and the faucet and the stove and so on. And now the rest of the solution comes by invoking the fact that you have previously solved the problem of how you take an empty pot and make boiling water. That's what reduction is. So we've reduced the NFA problem to a DFA problem. So we didn't have to talk about simulation anymore because that was all in the DFA solution. Okay. Let me give you another problem that is decidable, and this one has a little bit more substance to it. EDFA. It's the set. Oh, actually, no. This is rather trivial, but we'll need this. A is a DFA, and L of A is empty. Okay. So A is a DFA, and the language accepted by A, remember what that was? We talked about that when we were talking about regular languages. The language, these are all the strings that A accepts, is empty. It means A never accepts, okay? So into the Turing machine comes a description of A. So we have some description of A. And the Turing machine will accept its input if the language that A accepts is empty, otherwise reject. Okay? Well, one idea that doesn't work is for M to simulate A on all possible inputs to A. We can have a Turing machine that simulates A. That's what we were talking about over there. I didn't give you the full details because I couldn't think of them. But there's a Turing machine. We can build a Turing machine that will simulate a DFA. And M can generate input. When we were generating numbers, strings in lexicographic order, if you remember that part of from last week, similarly, M can generate strings that might be input to A. And then it can simulate A on each one of those strings and see whether or not A accepts or rejects. If A ever accepts, then M should accept. But what happens if in fact, I'm sorry, if A ever accepts, then M should reject, right? But what happens if in fact L of A is empty? Okay, so on every input that M generates, A will reject it, and we'll just keep going forever, and M will never know that it should ultimately accept, right? So that's not going to work, okay? Yeah. Okay, so that's not going to work. So what is going to work? Anybody have an idea? Well, if you look at the diagram for any DFA, you have a start state Q0, and then it goes over to some state, some other state on various input, and so on. Okay, so you have, some picture like that, and then ultimately some accept state. And what would it mean for L of A to be empty is that from Q0 there's no way of getting to any accept state. All right? So LA equals that if and only if there is no directed path in the diagram for A from the start state to a state in F. Because if there is a path, whatever, if there's some path from the start state to one of the accept states, then the string that gets specified along that path, or a string, there may be some choices here, any string that gets specified along that path is a string that A accepts, and therefore it's a string in L of A. Okay? So what it means for L of A to be empty is that there's just no way of getting to the accept state, or any accept state. But this is really kind of a trivial point. If there was no way whatsoever of getting to an accept state, then this is now a DFA that where L of A is empty. Okay, so when you're presented with a DFA, a description of a DFA, you can tell whether or not L of A is empty by just writing out its diagram here and seeing whether there's a path. Now, your intuition about what you can do with a Turing machine should tell you that when a Turing machine is given a symbolic description of A, it can, in effect, see whether or not there's a path on the diagram that goes from an accept state, the accept state, to a final state, even though it's not physically working on a diagram. It doesn't have a diagram in front of it. But what in effect can it do? It can mark, okay, Q0 has been reached. And then it looks to the transition rules and sees what can you reach from Q0. Okay, on A you can reach this state. On B you can reach this state. Okay, what can you reach from this state? Well, on B or C you can reach this state. From here you can reach that state. And then either the Turing machine at that point says there's no further states that can be reached, in which case no final state has been reached, or if the transition functions are different, then from here it can reach a final state. And whenever it's reaching a new state, it checks whether that's a final state or not. All of that sort of hand-waving idea or algorithm that I just specified, your intuition as now experienced Turing machine programmers, you should be able to say, oh yeah, of course I could build a Turing machine that could do all the things I was just describing at a high level. And therefore, there's a Turing machine that can take in A and find out and determine yes or no, accept or reject, is there a path from the input state to a final state in the diagram, even though the Turing machine doesn't have the diagram. The Turing machine is working on symbols, not on pictures. Okay? So the question of whether or not the language is empty is decidable. So EDFA is decidable. There is a Turing machine that can take in the description of any DFA and decide whether that DFA ever accepts anything or the language it accepts is empty. All right. Now, get to something that's actually non-trivial and much more interesting. But it uses all of these things. It uses these kinds of things as tools. EQ DFA equals AB, A and B are DFAs, and LA equals LB. Okay? So this is the equivalence question. So this kind of thing happens all the time, at least when you're grading homeworks. You know, your assignment is go out and write a DFA, create a DFA for some language. And one person comes up with, you know, some particular DFA with transition rules and diagrams. It's, you know, complicated and whatever, and somebody else comes up with a different one. Okay? There certainly are lots of different DFAs one can create for the same language. And the grader, at least, wants to know, are these both correct? Are they equivalent? Do they always accept the same strings and always reject the same strings? Okay, the language that's accepted by that's decided by one DFA, is it the same as the language decided, recognized by the other DFA? Okay? So everybody see what the question is? And this general kind of question is of some importance when you talk about programs, okay, which we'll get to later. If you have two programs and you want to know, are they equivalent? Do they do exactly the same thing? So if you formalize the notion of what a program does as it takes in some input and that it either accepts it or rejects it, do these two programs accept exactly the same set of input, and do they reject exactly the same set of input? Are the programs equivalent? Do they do the same thing? Well, that's something that's a very important question. If you think of functions even, you have some program that's calculating some function, and now somebody else comes up with another program that they say is faster, smaller, more patentable, which means you can make money off of it and use it less. This is a kind of a side rant. My research group yesterday was talking about something called arithmetic encoding, which is very, very interesting and valuable. And then they made the comment, the person presenting made the comment that it's not actually used much in practice, not because it's not a good idea, but because IBM holds all these patents to the algorithm, and therefore very few people can actually use it because they have to pay royalties. It's kind of a sick idea. But at any rate, we have these two functions, one that's patented and one that's not. But you want to know, do they actually do the same thing? Do they do the, you know, or two programs, are they both really computing the same function? Well, this is that question, but in the context of DFAs. Are the two DFAs the same? Okay. So, everybody know how to do this? Any ideas? Good. Yeah. So another side story. When I was an undergraduate taking this class, not here, but at Berkeley, this was a midterm question. And we hadn't even seen anything about equivalence or any, I mean, it was at the same stage that you were like 2 weeks ago. And this was on the midterm. Show how you can decide this. Nobody got it right. There was nobody was able to do it. I was the only student who had an idea of how to do it, but I couldn't, and it actually was right. And it's not the one I'm going to show you. But I couldn't get it finished in time. Anyway, we all got zeros for that. But that's the first and last time that I actually complained about a grade, because out of all the students, I was the only one who at least had an idea of how to do it, even though I couldn't get it done in time. Well, all right. I'm really going off on tangents today. Okay, so how do we do this? So here's what the professor when I was taking this class, wanted us to come up with during a midterm, even though we'd never seen any of this stuff. So let's define another language, LC, as this one, LA intersect LB bar. I'm not quite finished with this yet, but let's think about this one. A is a regular language. B is a regular language because there's a DFA that accepts A and B. So we know these are regular. L of A and L of B are regular. This is the complement of L of B. Okay? So these are the strings that are not accepted, that are not in language B. Okay? Is L of B bar, or the complement of L of B, is that regular? Yes. You all know that that's regular. You did it as a homework. Okay? The complement of a regular language is regular. You just take the DFA for B and you change the accepts and reject states, and you have a DFA for the complement of B. Okay? So now we have, this is a regular language and this is a regular language. And this is the intersection. The intersection of two regular languages is regular, right? So there's a DFA for this. Okay? Now, what is this in more words? What is this language? Again, I'm not finished quite, but just this part. What is this part sort of in terms of words?
The empty set, ideally.
It's the what?
It's the empty set if A and B are equivalent.
Well, you're jumping ahead. Yeah, it's not quite that, but you're jumping ahead. But right now I just want a sort of an English description of what this is. Yeah.
So that A accepts and B doesn't?
Yeah, these are the strings. What's in here, this is the language of strings that are accepted by A but not accepted by B. Okay, so here we have, if I make this Venn diagram, here's LA, here's LB. Okay, so what that is so far, it's the things that are accepted by A but not accepted by B. So it excludes this part in the middle. Okay? All right. Now I'm going to take the union with LA bar intersect LB. Okay? So in terms of this diagram, this is the things that are in B but not in A. Okay? And this is the union of those two. All right? All right. So L of C, is that a regular language? Yeah, that's regular because we know this is regular, and the union is regular. Okay, the union of two regular languages is regular. So L of C is regular. Okay, then somebody earlier said A and B are equivalent if and only if L of C is empty. Okay? A and B are equivalent. Well, what does equivalent mean? It means that everything that's in L of A is in L of B, and everything that's in L of B is in L of A. Okay? It means that these two should be identical. L of A and L of B should be the same circle, so that there should be nothing that's accepted by A but not by B, and there should be nothing that's accepted by B but not by A. Okay? So A and B are equivalent if and only if L of C is empty. This is the critical observation. And again, the proof of that is just what I said over here. Just look at this Venn diagram. This is the diagram for what L of C is. And equivalence means that the two circles should be the same. But if the two circles are the same, then there's nothing in L of A that's not in L of B, and there's nothing in L of B that's not in L of A. So L of C should be empty. And conversely, if L of C is empty, then, well, just say what I just said backwards. So look at the Venn diagram for L of C. Okay? So, now back to this question. EQ-DFA, is it decidable? This is a language. It's a language whose input consists of the description of two DFAs. And that particular input, the description of two DFAs, will be accepted if and only if A and B are equivalent, if L of A is equal to L of B. Okay? So the proof, I'll rewrite the theorem, EQ-DFA is decidable. How do we do it? How do we prove that EQ-DFA is decidable? What is the Turing machine that is going to be able to decide? It's a Turing. We need a Turing machine that can take in the description of two DFAs and determine whether those the languages accepted, or recognized, the languages that are recognized by those two DFAs are the same. So M takes in the description of the two DFAs, okay, and creates, if you like, a description of C. How do you create a description of this language C? Oh, sorry, L of C. No, sorry, description of C. C is a. So L of C here I described as a language, but now C, what is C? It's a DFA that recognizes L of C. Okay. How do you get, let's say now you, not you as a Turing machine, but you as a human, as a student, how would you build the DFA that recognizes L of C? Now this is a midterm question. This is definitely a legitimate midterm question. If I said, here's what L of C is, now describe how you could actually find the DFA for C. I mean, you have the DFA for A and B. Yeah?
Maybe if you process all three of them at the same time and you accept it if...
Did you say concatenate?
What's that?
I missed the key word in that.
Oh, just like in doing them in parallel, kind of. And, well, basically you just want to accept it. I'm not sure how to actually, like, write it out, but you want to run both A and B and only accept it into the language C if only one of them, kind of like an exclusive or...
Yeah, maybe, but you're thinking too much. You're overthinking it. Yeah.
We saw how to go from a Turing machine to its complement by swapping the accept, a DFA to its complement by swapping the accept and reject states, and we saw how to go from two DFAs to the intersection
Right.
by combining both of them to be simulated at the same time. And so you could just implement both of those transformations in the Turing machine. Hopefully.
Right. Yeah, you're using your tools instead of, that's what we want to do here. We do want to use our brains too, but whenever possible, if we have our tool, we should use the tool too. So you were using your brain and you were using your tool, you probably would get to the same place. But use your tools. We already have a tool. We already know algorithmically how to create the complement of a language. In fact, I just told you the algorithm, you interchange the accept and reject states. We already have a tool which creates the intersection. If we have a DFA for A and a DFA for B, we already have an algorithm that creates a DFA for the intersection of the two languages. And now it would be a DFA for L of B. Okay? Remember what that algorithm or that method that could create that DFA was developed. It was partly in your homework, I guess, but anyway, we did it in class, and we saw an algorithm for creating the union. If we have a DFA for some regular language and another DFA for another regular language, the DFA for the union of those two languages, we know how to construct that algorithmically. So we have a constructive way, people have a constructive way of building a DFA for L of C, this language that's recognized by C. So we have a DFA, we have a mechanistic way for creating the DFA C. Okay, and that mechanistic way can be translated, can be implemented on a Turing machine. It would be very, very tedious, not only as a homework exercise, but something to keep you busy for a long time, to ask you to find the complete Turing machine specification of that. But a Turing machine can be constructed that takes in the descriptions of these two DFAs and creates a description of that DFA C that we're talking about over there. Okay? And then what should this Turing machine do now that it has a description of C? Well, based on this, right, now M decides if L of C is empty. Okay? How does M decide if L of C is empty? I've even forgotten, but it was only a half an hour ago. We had it up here. Okay? Yeah.
You already proved EDFA?
It's what?
You already proved EDFA?
Right. Yeah, we've already proven the emptiness question for any DFA. So once the Turing machine has the description of the DFA C, then of course it can decide, because we've already done it, whether L of C is empty. And then based on whether L of C is empty or not, it accepts or rejects appropriately based on this comment here. Okay? So this is non-trivial, and we're using our tools as opposed to just doing it from scratch. Okay. How many were with me that this would be a very unfair question on a midterm? Anyway, you can see 30 years later I'm still smarting over that. And later I'll tell you how I thought of doing this during the midterm. And actually it was I think we had specific A's and B's. And so I thought of a method to do that, and it was right, but I just couldn't work it out on that specific A and B in time. Okay. All right, so now we can take it up a notch. All these questions about DFAs, we can ask equivalent kinds of questions about context-free languages, right? So if in there, we could either be talking about PDAs or we could talk about grammars. And we're going to just talk about grammars, but you can do the same about PDAs if you wish. Okay, so one particular question is for language A, CFG, GW, G is a grammar, that generates W. Okay, so into the Turing machine comes the grammar and a string W. And you want to know, does that grammar generate W? Now this is easier to think about even than DFAs as the input, because clearly grammars are strings. Okay? A DFA was specified ultimately by strings, but it kind of looks like a box. But a grammar is just clearly just a set of strings. So the input to the Turing machine that's going to be involved in here is a set of strings, or you can think of it as one long string if you have a delimiter, and then another string W. And you just want to know, is G a grammar that generates W? And I guess I should have said context-free grammar that generates W. Okay, theorem A CFG is decidable. And so there is a Turing machine, which generally, you can think of sort of as a general parser. It can take in the grammar involved and some input W and decide, accept or reject. Can W be parsed by this grammar G? Can G generate W? That's one direction of that question. The other opposite question is, can W be parsed by this grammar? Okay. And there's a Turing machine, a single Turing machine that can take in any context-free grammar and decide that, accept or reject. Now the proof of this uses more things about context-free grammars than we actually looked at and learned when we were talking about context-free grammars. So I'm not going to go through the proof of this because it then would bring us back into talking more deeply about context-free grammars than we wanted to. But I just want to point that out, that this is decidable, and it's sort of the equivalent question of given a finite state machine, a DFA, did that DFA accept, and some input, would the DFA accept that input? So that's decidable in context-free. Okay. Similarly, the equivalence question is decidable for context-free languages. EQ, CFG, G and H. So we have two grammars, G and H, those are context-free grammars, and the set of strings that G, the grammar G generates, is equal to the set of strings that grammar H generates. So those two grammars are equivalent. And again, this is a very relevant kind of task that in compilers or programming language theory or any kind of language processing, you would be interested in being able to answer. So you can build a single Turing machine which can take in two descriptions of two context-free grammars and figure out whether or not those two languages are the same. Okay, and again, I'm not going to give you any of the details of this, but you should, given what we talked about here, start being able to piece together some of the components of how you would prove this. Okay, and then finally, for context-free grammars. Every context-free language is decidable. Okay, and that means that the input, again, given G and W, the Turing machine can decide if G generates W. Okay, so it would either say yes or no, accept or reject. And so basically, what this is saying is that any context-free grammar or any context-free language grammar can be implemented and then simulated on a Turing machine. So actually today, although I started out by saying we're going to get to things that Turing machines can't do and interpret that as problems that can't be solved by an algorithm, what we've actually looked at today are problems that can be solved by a Turing machine, languages that can be decided by a Turing machine. So I only got through half of my notes. But this is for the purpose, seeing what Turing machines can decide is first of all useful if, for example, this is quite useful, or the equivalence between two context-free grammars is useful because there are a lot of problems where the languages you're dealing with are context-free, and the kind of manipulations you want to do on those languages are doable by a Turing machine, which means they're doable in C, on your iPad or whatever. And it's useful because we've introduced this notion of a Turing machine that takes in as description some other machine or a grammar. Okay, and we're going to get to Turing machines taking in descriptions of Turing machines. That's the natural next step. So we have that. We learned that today, and we learned a little bit about reduction and so on. So we're working up to where next time I'm going to show you that there are languages that are not Turing recognizable. There are languages that are not Turing decidable. And first, the existence of those languages, we'll prove those, and then we'll prove specific languages that are not Turing recognizable or Turing decidable.